Alright, in this last video I want to go through a quick MATLAB demonstration. And what we were just talking about, we had an example where there's two lines separated by pi over 10. So that's the frequency difference between the two sinusoids. We decided that when we did this analysis of these two sinc functions that overlap, that we need the number of samples to be about 20. If we need to observe 20 samples in order to see two spectral lines, and this is a really rough kind of an estimate, but it gives us a place to start, because otherwise we wouldn't know if we needed 20 or 2,000. So this gives us an idea of how many samples we need for this particular example. So I pulled up a MATLAB window, and here's a little MATLAB script that I've got in the MATLAB editor, and you can see that we're going to generate these two sinusoids. There's the first two frequencies, 3 pi over 10 and 4 pi over 10. Let's change this to 20, which is the value that we predicted that we'd need. We'll go back to 20 here in a second, or back to 15 in a minute. But we're gonna make 20 observations of these sinusoids. So there's a signal. X is cos omega 1 n plus cos omega 2n. And n is going to go from 0 to n minus 1, and n is 20. And then let's just we're also going to plot the original signal. So let's do that. And I'm going to hit F9 key, and we're going to see what 20 samples of this thing looks like. Okay, so here's 20 samples of these two sinusoids added together, and it doesn't look like much. It's only 20 samples, and yet from this we're going to try to figure out what the spectrum looks like. We're going to see if there's two signals or maybe four sinusoids. Who knows? But it's an awful small amount of data. Okay, so let's take the fast Fourier transform of that. I'm going to do it right here. Just take the FFT. So that'll be 20. There's 20 data points in X, and we're just going to plot real quick and dirty plot. And this is what we get. I didn't even bother to label the frequency axis, but the indices go up to 20. So this is the FFT. There's 20 points, and you can see that, and this is the image that we don't have to worry about. It's above the folding frequency, and we definitely do not have two spectral lines present here. Okay. Well, let's have a look at this with with some zero padding. So I'm going to zero pad out to 128, and then we're going to plot it. And also, I'm going to I'd hate to move this cursor around because it'll flash up some data that I want, but I'm going to plot an asterisk at omega 1 and at omega 2 at those frequencies with an amplitude of 6, just to see where those two frequencies are on the spectrum. So I'm going to hit the F9 key. And you see what zero padding has done for us. Zero padding has filled in all of those data points, or has interpolated between those things that we saw last time, and we actually can now see that there's two lines present. There's two spectral components here. Here, these two asterisks indicate the frequencies that we're trying to find. So those are the perfect frequencies. Okay, so we should have peaks. The peak of this should have the same frequency as the ideal frequency. Now what's going to happen is there's all kinds of interference between this sinc function and its side lobes, constructively and destructively interfering with this sinc function and its side lobes. So we're going to see something called spectral bias, where the peak here may be a little bit shifted from the actual frequency. That's called estimation error, a bias estimation error. Okay, so let's look at another case. So we can, with n equals 20, we can actually see, we can resolve these two spectral lines. Let's see how small we can make n. Alright, back in MATLAB, let's make it to Let's make it 13. Now we're only going to have 13 samples of the sum of these two cosines here. Okay, so we're going to only measure this for 13 values, and then we're going to take the fast Fourier transform of that. All right, so let me hit F9, and we can see what 13 values looks like. This is the sum of the two sinusoids. There's not much there, so it's hard to believe that we could detect anything. Now I'm going to, well, let's just go ahead and plot the zero padded version of that. So we still only have 13 samples, but we're going to zero pad out to 128. And this is what we get. Okay, so we can no longer detect that there's two sinusoids present. There's not two lines. Those are the places where we'd see them, but they're smeared together. Remember the two sinc functions. The smearing idea is causing us to not have enough resolution to resolve these two lines. Okay, well, let's go up a little higher. Let's go up to 14. And I'll just plot all of those. I'm going to hit F9. And now you can see, okay, with 14, well, we still can't resolve those two spectral lines. Okay, now we're going to try 15. There's 15, and I'm going to hit F9. And now with 15, all of a sudden we're able to see the two lines start to show up. They aren't really distinct, but they're starting to be distinct. So the difference between 13 and 15 is really, really significant. And it's really hard to tell when exactly what values will cause us to be able to see the two lines coming through, because like I said, it depends on the phases, depends on the cancellation and destructive and constructive interference. But when we found n equals 20, which is 2 pi over the frequency separation, that gave us a starting point, and then we have to sort of change up and down, trial and error, see what value of n actually allows us to resolve the two spectral lines. And it looks like this particular value of n works for us. So that's the smallest value of n that we could, so n is 15, is the smallest value of n that resolves the two lines. And one last thing I point out again, there still seems to be some frequency bias here where the peak is not lined up at the same frequency as the original frequency. Okay, one more picture here. This shows when I went up to n equals 30, that now for this case it looks like the peaks are indeed lined up with the actual frequencies. So this peak is lined up with that frequency. So if we make n large enough, we can reduce the bias, the error in frequency estimation. So anyway, that's the end of this demo.